Hello. In an earlier video on correlation, we came to understand that different data types and mixes of data types require different ways of calculating their level of association or correlation. So in this video, I will cover a brief recap of what correlation is for those viewers who haven't seen my video on correlation, a brief recap of different data types, a matrix of measures of association, and examples of using the matrix on different data types. The examples shown here have been produced in R. Of course, the same methods can be deployed in Python. To make the most of this channel, subscribe now. Correlation can be defined as the statistical relationship or association between paired variables x, y. To understand what is meant by paired variables, let's look at a snippet of data. Here there are two variables, percent rental accommodation and percent unemployment, which have been measured for each postcode sector. Paired variables are measures of the same place, the same individual, or at the same time. If the variables are not paired, then correlation can't be used. A correlation coefficient quantifies the strength of a relationship or level of association between paired variables. Conventionally, a correlation coefficient is in the range -1 to +1, where +1 indicates a perfect positive match between two variables, and -1 indicates a perfect inverse or negative match between two variables. A correlation coefficient of 0 indicates no relationship between two variables, and are random in relation to each other. Conventionally, data types are classified as nominal, ordinal, interval, and ratio. Nominal, also referred to as categorical, is where objects are classified into named groups, for example gender, days of the week. Where there are only two classes of object, the data can be referred to as dichotomous. Ordinal is where objects are ranked in some order, for example from smallest to largest, or from disagree to agree in Likert scales. Interval is where objects are measured according to a scale, and has both an arbitrary 0 point and an arbitrary interval, for example measures of temperature. Thus 0 degrees centigrade equals 32 degrees Fahrenheit equals 491.67 degrees Rankine. Ratio is where objects are measured against an absolute 0 and where relative ratios are preserved. For example, speed. 0 kilometers per hour is absolute, and 60 kilometers per hour is twice as fast as 30, which in turn is twice as fast as 15 kilometers per hour. Other data types needing special consideration, but not used in this video, are direction, where the measurement is circular, reference systems, for example map coordinates, and timestamps, date and time, which can be treated as linear or circular. When analyzing data, we often deal with variables being a range of data types. Thus, for a correlation R, X, Y, variables X and Y may be the same or different data types, and depending on the combination of data types, different methods need to be used. The commonly used Pearson formula is only suitable where both variables are interval or ratio data. You should not be using Pearson for nominal or ordinal data. Further considerations need to be taken into account, for example such as whether the nominal variable are dichotomous or not, and whether the ordinal variables summarize a normal distribution or not. Appropriate methods for different combinations of data types are shown here. This is just a selection, as there exists out there yet more measures of association that could be used. Here is a questionnaire dataset we are going to use. It's rather old, but it has a range of data types and therefore serves our purpose. The first attribute is a unique ID, and although coded as a number, is actually nominal. The ID is just an identifier to anonymize the responses, and for the purpose of analysis can be omitted. Of the remaining 22 variables, there are 8 nominal variables, 3 of which are dichotomous, 13 ordinal variables, 1 of which is dichotomous, 9 are Likert scale responses, and just 2 numerical variables. Before we can analyze the data, we need to structure the variables into their respective data types, so they will be handled properly. This step is very important, yet often overlooked in the rush to get some results. There are 22 variables and 151 questionnaire responses. Note the NAs denoting missing data. This is important to reflect on when doing correlation, as we are dealing with paired data. NAs will reduce the number of pairs, n, available for calculating correlations, so we must analyze the prevalence of NAs. Here is a missingness map, which, as its name suggests, shows where all the missing data are. One respondent has given no answers to all questions and should be deleted from the data, giving n equals 150. Some variables have a lot of missing data because respondents didn't answer the question. The variable politics with NA equals 61 has proved unpopular. We will now go through the matrix of measures of association by giving an example of each. The key bits of our script are given, as well as the results in bold, along with any tables and graphics that may aid understanding. This is phi for 2 dichotomous nominal variables. Par deg, does either parent have a university degree, yes or no, and family, employment class of main breadwinner, manual or professional. Due to missing data in the variable family, there are 144 data pairs instead of 150. Phi is in the range -1 to +1. In this case, phi equals 0.46. This is perhaps evident from the table and circular plot, where the vast majority of manual has no degree, whereas professional is roughly 50-50, no degree and yes degree. The histogram shows the result of the bootstrap, from which the 95% confidence intervals are derived. Kramer's V can be used where one or both variables are multinomial. Due to missing data in the variable entry, there are 144 data pairs instead of 150. As an observation, the table and the circular plot show a bias towards female respondents, being 80% of the questionnaire data. Unlike other measures of association, Kramer's V is only in the range 0 to 1. The result 0.2267 shows that only 23% of the entry data can be ascribed to the association with gender. The 95% confidence interval is from the bootstrap. Rank by serial coefficient measures the association between a dichotomous nominal variable and an ordinal variable, and is in the range -1 to +1. The dichotomous nominal variable is family, employment class of main breadwinner, and the ordinal variable is expected earnings in 10 years' time. Due to missing data in both variables, there are 122 data pairs instead of 150. The result is minus 0.381. The ordinal data has been split into the two dichotomous classes. A result of 0 means no difference between them. Positive values mean that the first group tends to have larger values than the second. Negative values mean that the second group tends to have larger values than the first. This is evident from the table, where the modal class of manual is less than that of professional in terms of ordinal variable expect, thus giving a negative association. The 95% confidence intervals are from the bootstrap. Kramer's V is again used for the larger contingency table, this time for the strength of association between age classes, age C, and basis of entry to university, entry. Due to missing data in the variable entry, there are 144 data pairs instead of 150. Remember, Kramer's V is in the range 0 to 1. The result is 0.4562. That is, 46% of the entry data can be ascribed to the association with age. Compare the modal age of A-level entry at age 18 to 21 with that of mature entry at age 31 and above. Again, the 95% confidence intervals are from the bootstrap. The point biserial coefficient calculates the level of association between a dichotomous nominal variable and a numerical variable. In this case, the dichotomous variable is family and the numerical variable is grades n. The result is a negative association of minus 0.38. For positive associations, the reference group of the dichotomous variable tends to be larger than the other group, and vice versa for negative associations. The coding of the family variable is manual equals 1 and professional equals 2. So family manual is the reference group. From the box plot we can see that family manual has a much lower median than family professional, and so the association is negative. The 95% confidence intervals are calculated using a function sigma r from Stack Exchange, where n equals the number of data pairs and p is the proportion of data pairs that are the reference group, taken from the box plots. The polychoric coefficient calculates the level of association between two ordinal variables. The assumption is that the data summarizes a normal distribution. In this example, the Likert scale variable at 3, politics is boring, and ordinal variable grade C are used. The correlation is minus 0.25 with 95% confidence interval of minus 0.27 and minus 0.23, which need to be calculated separately. For the test of bivariate normality, the null hypothesis is that the data are sampled from a Gaussian distribution. If the p-value is small enough, conventionally 0.05 or less, the null hypothesis can be rejected, and thus the alternative hypothesis that the data are not sampled from a Gaussian population can be accepted. In this example, p equals 0.19, so the assumption that the data summarizes a normal distribution can be met. Kendall's tau can be used to calculate the correlation between two ordinal variables where no assumptions are made about the distribution of the data. In this example, the Likert scale variable at 2, I enjoy watching soaps on the television, and ordinal variable age C are used. The correlation is minus 0.23. The command core.test is core R and doesn't need a particular library. The command requires as numeric data rather than ordered factors. There is no option to calculate 95% confidence intervals. However, the command does test the null hypothesis that tau equals zero correlation. In this example, the null hypothesis can be safely rejected. The polyserial coefficient calculates the range of association between an ordinal and a numerical variable. The assumption is that the data summarizes a normal distribution. In this example, the Likert scale attribute @3, politics is boring, and numerical variable grades n are used. The correlation is minus 0.22, a 95% confidence interval of minus 0.23 and minus 0.21, which need to be calculated separately. For the test of bivariate normality, the null hypothesis is that the data are sampled from a Gaussian distribution. If the p-value is small enough, conventionally 0.05 or less, the null hypothesis can be rejected, and thus the alternative hypothesis that the data are not sampled from a Gaussian population can be accepted. In this example, p is less than 0.001. And so the null hypothesis can be safely rejected, which comes as no surprise when we see the histogram for grades n. This example has failed the test of normality, and so the coefficients and its 95% confidence intervals may not be reliable. Better use Kendall's tau. This repeats the previous example, this time using Kendall's tau, so no distribution assumptions need be made. This gives a much lower correlation coefficient of minus 0.14. Notwithstanding this, the null hypothesis that tau equals zero correlation, can be safely rejected, and we can accept there is a small level of negative association between @3, politics is boring, and grades n. Spearman's rank correlation coefficient, ρ, is for numerical variables. At the same time, this uses ranks instead of actual values, and should be used for small samples or skewed data. The command core.test is used. There are only two numerical variables in our example dataset, grades n and age n. The result is a very small correlation of 0.05, which ought to be ignored because the null hypothesis that ρ equals 0 can't be safely rejected. P-value is greater than 0.05. The same example with grades n and age n are now repeated using Pearson's product moment correlation coefficient. This assumes the data are normally distributed. The command core.test is used. The result is again a very small correlation of 0.06, which ought to be ignored because the null hypothesis that the true correlation equals 0 can't be safely rejected. P-value greater than 0.05. Not only that, the 95% confidence interval of minus 0.1 and plus 0.2 straddles 0. This should be of no surprise when we look at the scatter plot, which shows a random scatter with no trend. Not all paired variables have a level of association worthy of further analysis. This YouTube channel will feature a growing number of videos on quantitative and qualitative analysis and on machine learning. These are based on 25 years of masterclasses. Subscribe now and look out for them. Also, you can obtain the slide decks and transcripts for the videos featured in our YouTube channel from Amazon.